In this video, we're going to continue our exploration of the use of arrays in programs, and we're going to do it in the context of a slightly fun kind of application. So this is an application that's been part of computer science for quite a long time. It's the application of cellular automata, and that's going to provide us with an opportunity not just to look at one-dimensional arrays, as we've looked at so far, but multi-dimensional arrays as well, in particular at two-dimensional arrays. But the principles that apply to two-dimensional arrays can be extended to further dimensions should that be required. A cellular automaton is a model of a very simple kind of cell. It's not a biological cell, although we often characterize the cell state as being alive or dead. We're not trying to imitate a particular organism. We're going to represent the cells of an automaton with an integer array, and the values stored in each element of that array represent the state of the cell at a particular point in time. We model the changes in a cellular automaton over a series of time steps, and at each step the state of a cell is reviewed and potentially updated. And typically the update is based upon the current state of the cell and the state of one or more of its neighbours. And there are various sets of rules that determine exactly how a cell's state changes according to how many neighbours it's got, what the various available states are, and so on. The type of automaton we're going to consider is particularly simple, but that will then allow us to focus on the array-based elements of our solution. At each step of the operation of the automaton, we want to consider what the next state of each cell will be within the automaton. So we are going to be iterating over the current state of the cells, and we will be creating a new array that's going to be storing the new state of each of those cells. In the type of automaton that we're going to be modelling, the state of a cell can only ever be 0 or 1. And the next state is calculated by taking the sum of the cell's current state and the states of its two neighbours. So we're going to be generating a sum that's in the range 0 to 3. But we're then going to take that sum modulo 2, which means that the resulting state again will be either 0 or 1. And the table here shows all the possible outcomes that there could be from the state of a particular cell and the state of its two neighbours, given the rule that we're going to be following. And the code at the top of the slide shows the way in which we'll make the calculations in order to calculate the next value of index I for the next state array, which will ultimately become the current state on the next step of the simulation. We're going to start the automaton in the state where all elements of the array contain the value 0, apart from the cell right in the middle of the array, and that will contain the value 1, indicating that that particular cell is alive. So there's a single alive cell within this automaton. For the next step, the process will involve iterating through the array, calculating the sum of the values in a single cell with those of its two neighbours, taking the sum modulo 2 and writing the new value into the appropriate element of the next state array. So these three cells all have a value 0, the sum for this cell will be 0, and therefore there will be 0 in the next cell. If we move along to this cell here, it's 0, one of its neighbours is also 0, but the other neighbour is 1. So the sum there is 1, taken modulo 2, results in a 1 being written into the next state element for this particular cell. If we consider this cell, we take its value, which is 1, the value of two of its neighbours, which are both 0, so the sum of those three is 1, again modulo 2 is 1. And we get the same effect over here, whereas all the remaining cells will have the value 0 written in here. If we consider what the state will be after the following step, then once again, across all these cells, we're going to get zeros. Here, we'll get a sum of 1, causing a 1 to be written here. In this particular case, we're going to get a sum of 2, so 0 plus 1 is 2, which when taken modulo 2 will result in 0, and that's why we have an empty cell here. Here we get a sum of 3, modulo 2 is 1, so we get a 1. Again here we get a 0, here we get a 1, and then zeros for all the remaining cells here. And that pattern continues step after step after step. And we can see that in practice if we take a look at the automaton project within BlueJ. So the project consists of the automaton itself, which implements all the rules we've just been describing, and an automaton controller that's responsible for stepping through and asking the automaton to update its state on each step. We can create an automaton controller. As you can see, the initial state of the automaton is that the single central cell has the value 1 and all the other cells have value 0. And now we can ask the automaton to run for some number of steps. We'll ask it to run for 20 steps. And you can see the progression as it runs through each step. So let's take a look at the source code that's responsible for implementing the automaton. You can see that we have an array of type integer, which we're calling state in this code, and that's created in the constructor for the appropriate number of cells that we require. Here we have an example of a for each loop iterating this time over an array. So up to this point we're used to seeing for each loops used to iterate over collections such as an array list. An array can equally be used in a for each loop, and what happens is that the loop's variable is set to the value of each particular item within the array on each iteration, and that value can then be probed inside the body of the loop, and we either print out a star for a live cell or a space for a dead cell. Let's take a look now at the code of the update method. So this is where the heart of the automaton is implemented. We start off by creating a new integer array that's going to receive the updated state of the cells ready for the beginning of the next step. And then we're going to iterate over our state array, and for each element in the array we want to calculate what its new state should be. So here we see inside the body of the loop that we're going to store in local variables left, center and right the states of the cell under consideration in center and the two of its neighbors. Now we have to be a little bit careful because there is no left neighbor for the item at index 0, and there is no right neighbor for the final element in the array. So we can't simply use i-1 and i+1 in order to access the left and the right neighbors without first checking to make sure that we're not going to fall off either the left-hand edge or the right-hand edge of the array. It turns out that this particular code is a little bit clunky. In other words, we're testing for two situations which are only going to occur either on the first iteration or the very last iteration. And in the chapter we actually discuss ways to avoid this slightly clunky code. But it will do for now, do for illustration purposes, and it makes the point that we want to gather the three values. We then want to sum them, take the result modulo 2, and then set element I of the next state array. And we'll do that for every single item in the state array, and then eventually the next state array will replace the original current state array ready for the next step within the simulation. So quite a number of useful array-based operations to consider there. This creation of a new array, the iteration of the array, checking for the boundaries of the array, and then accessing elements referenced to the left or to the right of a particular element, and the storage of a new value into the next state array. So there's quite a lot of array-based code worth studying in this example. Now, something you might have noticed when we were looking at the method to print out the current state of the automaton was we had an if statement where we're checking to see whether the value of a cell is 1, and if it is, print one particular character, but if the value is 0, we want to print a different character. That's quite a lot of code in order simply to print either one character or another character. And there's an operator in Java that allows us to more concisely express the selection of one value or another based upon a Boolean condition. So this is called the conditional operator, and we can see that that whole if statement can be expressed much more concisely by looking at the parameter of the print call in the code at the bottom of the slide. So the Boolean expression is cell value equal to 1 is evaluated, and if it is, then the expression immediately following the question mark is the result of that, and we'll end up printing a star. But if the Boolean expression is false, then the value immediately after the colon character is selected, and it will be a space that's printed. So the if statement and the print in the lower piece of code are entirely equivalent. In the lower piece of code, we've wrapped that within the for each loop in order to illustrate how it would be used in practice to print out the current state of an automaton. So the conditional operator is something it's worth being aware of. There are often cases where instead of writing an if-else statement, it's more concise to use the conditional operator. So up to this point, all of the arrays that we've considered have been what we might call one-dimensional arrays. Java supports multi-dimensional arrays. It would be unusual to go much beyond 2 dimensions, although Java does support many dimensions if required. But it's not uncommon to want to have 2-dimensional arrays. So 2-dimensional arrays might be used for things like representing matrices in mathematical applications, or boards in applications involving games. So a 2-dimensional array in effect gives us a grid or a table. The way that Java implements multi-dimensional arrays is actually they're considered to be arrays of arrays. So the rows in a 2-dimensional array are actually 1-dimensional arrays. Let's look at one of the ways in which we might use a 2-dimensional array in order to represent a more sophisticated cellular automaton. The one we're going to look at is what's known as Brian's brain, and it's called that because it was devised by Brian Silverman. In this case, rather than having only 2 possible states, a cell may have 3 possible states, and we typically refer to those as alive, dying, or dead. Although it should be borne in mind that we're not representing real organisms. These are simply convenience values that are probably going to be represented by numerical values such as 0, 1, and 2 in the implementation code. So don't become too focused on the idea that we're somehow representing real living creatures, for instance. Now, because we're going to be working with a 2-dimensional array, we can have a much more sophisticated set of neighborhood cells. And for Brian's brain, we're going to use what's called the Moore neighborhood. So each cell within the grid will have 8 neighbors, 2 above, 2 to the sides, and 4 diagonally. So a potentially quite complex combination of those neighborhood states could be employed in order to determine what the new state of an individual cell is going to be within the grid. So let's look at our implementation in terms of the visualization that it provides. And this, I think, is quite a fun project to play around with. Here's the project. Because it's a more sophisticated application, then we actually define a class to represent the various states and the various state transitions that an individual cell can undertake. So we can create an environment, and then we've got some controls that allow us to run the animation, control the animation's speed, step, pause, and reset, and so on. So to start off with, let's just step through individually and see how the states of the various cells are going to be updated. So you can see that the visualization contains 3 different colors representing the 3 different states that each cell can take on. And as we step on through, we see that changes begin to take place within the visualization as the cells interact with their neighbours in their Moore neighbourhood. Now, it's a little difficult to see the long-term effects of these changes, but we can select Run and then see a series of steps taking place in which interactions between the various cells take place. And what's interesting to note is that the interactions give the impression of shapes moving within the space. Although this is simply an artifact of the interaction, there's no movement physically taking place within the individual cells within the environment. But you get some really quite nice effects happening. And long term, you can see that various shapes emerge, appear to move backwards and forwards across the grid, up and down and so on. And then occasionally you get to a state where there are no further changes possible. We can reset, we can randomize, and we can run again to see a different set of simulation interactions. And this is all quite fun. So there's plenty of detail in the book about how that project is implemented, but let's at least just take a look at some of the basics of how we can represent two-dimensional arrays within Java. So here we've got the declaration of a variable called cells, and because it's going to be a two-dimensional array object that it refers to, we have two pairs of square brackets immediately after the type name. So cells is going to be a variable that refers to an object. The object is going to be a two-dimensional array of cell objects, or in other words, an array of cell objects. And then we can see the creation of that two-dimensional array in the next statement. So we say new cell, and then between the two separate pairs of square brackets, we ask for the particular dimensions, the number of rows and the number of columns that this array is to contain. It's important to bear in mind that all we have at the point where we've created the array is the ability to store that number of cell objects. Creating the array doesn't create any cell objects itself. Creation of the cell objects requires a separate step, and we've encoded that within two nested for loops, where we firstly iterate over the number of rows, and for each row we iterate over the number of columns, and then for that row-column combination we then create a new cell and store a reference to that new cell object in that particular element of the two-dimensional cell array. So this form of nested for loop is very common when working with two-dimensional structures such as a two-dimensional array. Iterate over the rows, iterate over the columns, and then use the current row value, the current column value, to access a single element within the two-dimensional structure. Just to illustrate the fact that a two-dimensional array is really an array of arrays, here's an alternative way of representing that particular initialization of the cells within the two-dimensional array. So the outer for loop is iterating over the index range for the rows, and then what we do inside the body of that first for loop is to access the array, the one-dimensional array, that's stored at that particular row element. So we've got a local variable nested inside the for loop called next row, and we assign to that the one-dimensional array of cells that's stored at that particular row location of the two-dimensional array. Then the nested for loop iterates over the column indices for that one-dimensional array and creates a cell object, and is now using single-dimension indexing to work just with that row array. So we only need one pair of square brackets after the name of the array because we're dealing with a single-dimensional array that is one of the rows within the two-dimensional array. So this more explicitly illustrates that a two-dimensional array is literally an array of arrays, where the first dimension selects a subarray and the second dimension then selects an element within that subarray. And one of the features of Java is that we can create two-dimensional arrays that are not necessarily rectangular. So potentially each row could have a different number of elements within it. We could individually allocate for each row a different size for the array that it's going to be storing. We're not using that feature here, and it's fairly unusual to use it, but it is a feature that it's possible to make use of within Java. So we've looked at a couple of examples of using both one-dimensional and two-dimensional arrays to provide some further practice and insights into the way that we often use arrays and their combinations with things like for loops, the use of indexing to index elements either side of a particular element within an array, the need to take care at the left-hand edge and the right-hand edge of an array to make sure that our index value is always valid.